Well, moving forward in this problem, now we have to find other things in this question. So primarily we just have to find three things. Number one is that we have to calculate angular momentum of the center of mass about the point O. Number two, we have to find angular momentum of this entire assembly about the center of mass. And number three, we have to find angular momentum of this entire assembly so that we can get its Z component, which they are asking in option A. So we are going to find the angular momentum of center of mass about the point O, which they are asking in option C. So let's see how we will find angular momentum of the center of mass about the point O. So let's say this is your center of mass C and this is point O, and this is your x-axis, this as your z-axis. I'm not drawing the wheels, I'm only drawing this center of mass. The distance O to C is already known to us, which is equal to 9L by 5. We have calculated it. This angle was theta. So we are just focusing on this center of mass and how it is moving. You know that at this moment the center of mass is going into the plane of the paper, that is towards the positive y-axis. So let's say the velocity of the center of mass is equal to v, which is into the plane of the paper. I'm denoting it by a cross sign, and we already know the value of sine theta, which was 1 by 5. Cos theta is equal to under root 24 by 5, and this L is equal to under root 24 times A. So let's find the angular momentum of center of mass about the point O. I'm going to denote it by L vector of COM. So when we have to find angular momentum of the center of mass, we have to treat that the entire mass of the entire assembly, which is equal to 5 times m, is concentrated at the center of mass, and its velocity is v, which is into the plane of the paper, and we want to calculate its angular momentum about the point O. So the formula that we are going to use is mvr perpendicular. So when we write the magnitude of angular momentum of center of mass about the point O, it is going to be mvr perpendicular. M is the mass, which is equal to 5 times m. V is the velocity of center of mass, which we have referred as velocity v, and r perpendicular is the perpendicular distance of this line of motion, which is into the plane of the paper from the point O. So you can see that the perpendicular distance to the line of motion from the point O is nothing but 9L by 5. So we have to get the value of this velocity v, and how we are going to do that? We know that this center of mass is revolving about the z-axis in a horizontal circular motion, and we have already calculated that angular velocity about the z-axis is equal to omega by 5, which we have already referred to it as alpha. So we can get the value of v quite easily from this, because v will be equal to the angular velocity about z-axis, which is omega by 5 times its distance from the z-axis. So its distance from the z-axis can be calculated from this geometry, which will come out to be 9L by 5 cos theta. So velocity of this center of mass becomes angular velocity, which is omega by 5 about z-axis times 9L by 5 cos theta. So we just have to put the value of this v in this equation. So we are going to get the value of angular momentum of center of mass as equal to 5m omega by 5 9L by 5 cos theta. We can write cos theta as under root 24 by 5. Then we have 9L by 5. So this is going to be the magnitude of angular momentum of center of mass about this point O. So we can simplify it, and in fact we can put the value of L as under root 24a. So when we do it and simplify it, we are going to get this value as 1944 under root 24 divided by 125 ma square omega. So this is going to be the magnitude of angular momentum of center of mass about the point O. And if we check the option C, in which according to them this value is 81 ma square omega, which is definitely not the case, and therefore this option C is going to be an incorrect. And now let's solve for this option B, in which we have to find angular momentum of this entire assembly about the center of mass. So let's see how we are going to find the angular momentum of this entire assembly about its center of mass. So in this assembly, this is where you have your center of mass, This is the x-axis, this is z-axis, and we already know that this entire assembly is rotating about this axis with an angular velocity omega, and this axis is also rotating about the z-axis with an angular speed omega by 5. So how we are going to find angular momentum of the entire assembly about the center of mass? Let us say that angular momentum, we are referring it as angular momentum with respect to center of mass. So let's try to visualize what is happening in the COM frame. So let's imagine that we have another frame whose origin is at the COM, and this is the x-axis in the frame of center of mass. This is a z-axis in the frame of center of mass, and you know that there is a y-axis in the frame of center of mass which is going into the plane of the paper. And if we try to visualize this assembly in this frame with respect to this center of mass C, then we will see that this assembly is going to have two angular velocity that we already know, because these two discs are rotating about this axle with an angular speed omega, because of which it has an angular velocity omega in this direction. And since this axle is also rotating about the z-axis, and therefore about this center of mass, this entire assembly is going to have an angular velocity omega by 5 towards the positive z direction. So it is going to have double angular velocity in the center of mass frame. And now we have to find angular momentum of this entire assembly about the center of mass. So do we have any formula for this? Well, we have studied one formula in which angular momentum with respect to center of mass is written as ICM times omega vector. So what is this ICM in that formula? ICM is the moment of inertia about the axis that passes through center of mass and is along this omega vector. So now we just have to think, can we make use of this formula in this particular problem? Because we have already seen that this is an unusual problem. Then let me tell you that we cannot make use of this formula in this particular problem. Why we can't use it? Well, it's because this is a problem in which you have two angular velocity of this assembly. About this axle, the two discs are rotating with angular speed omega, and this axle is also rotating. As I already mentioned, that this is the rarest of the problems that usually IITs ask, in which the entire assembly is having two angular velocity. So if you sit at the center of mass, what you will visualize, you will see that the smaller disc is rotating with angular velocity omega about this axle, and also that this smaller disc is rotating about the z-axis like this, and similarly this bigger disc is also going to rotate about the z-axis like this, in addition to the angular velocity that it already has. So with respect to center of mass, this is a smaller disc which is rotating with angular velocity omega, and also that this smaller disc is rotating about the z-axis like this. And similarly, you have a bigger disc which is also rotating about this axis with angular velocity omega, and the entire disc is also rotating about the z-axis with an angular speed omega by 5. Alternatively, you can also visualize it in this manner, that when you sit at the center of mass, this entire assembly is having an angular velocity in this direction omega, and this angular velocity vector is also rotating about z-axis with an angular speed omega by 5, which means that the net angular velocity will be the vector sum of these two angular velocities, which will be this omega vector and this omega by 5 vector, and the vector sum is going to be in this direction, which is going to be net angular velocity vector. Even alternatively, you can visualize it in this manner, that this is the omega net vector of the entire assembly at this particular moment. And definitely this omega net vector is not going to remain constant with respect to its direction. This omega net is going to rotate about the z-axis, and therefore in this situation you just memorize that this particular relation, that angular momentum with respect to center of mass equal to ICM omega, cannot be used. So now the question is, if we cannot use this formula, then how we are going to find angular momentum of this entire arrangement with respect to center of mass? Well, in that case, you have to calculate angular momentum of an elemental mass with respect to center of mass, and then you have to integrate it, and definitely that is going to be very difficult process. Well, I have an alternate method in order to solve this, so let us talk about that alternate method. So the alternate method goes like this, that this is the center of mass of this entire assembly. Just write the two angular velocity vector. This is going to be the first angular velocity vector omega. This is going to be the another angular velocity vector omega by 5. Now you have to identify two principal axes of this assembly. So one of the principal axis will be along this axle. I'm going to call this principal axis as axis number 1, and another principal axis will be perpendicular to this axis and passing through center of mass, and so this is going to be your second principal axis. So the angular momentum with respect to center of mass is going to be I1 omega 1 1 cap plus I2 omega 2 2 cap. Now what is this I1 omega 1, I2 omega 2 1 cap and 2 cap? Well, I1 is the moment of inertia about the first principal axis of this entire assembly, and I2 is the moment of inertia of this entire assembly about the second principal axis. What is omega 1? Omega 1 is the angular velocity along the first principal axis, and omega 2 is the angular velocity along the second principal axis, and 1 cap is the unit vector in the direction of the first principal axis, which is, let's say, in this direction, this is 1 cap, and 2 cap is a unit vector in the direction of second principal axis, let's say, which is in this direction, this is 2 cap. Well, I'm not showing it over here from where we got this result, but you just need to memorize. As far as IIT is concerned, we don't need to inquire into the part from where we got this result, as very rarely we are going to make use of this result. So all you just now need to do is to calculate the value of I1, I2, omega 1 and omega 2. So what will be the value of I1? It's very easy. I1 will be equal to moment of inertia of the smaller disk about the first principal axis plus moment of inertia of the bigger disk about the first principal axis. So for the smaller disk, it's very easy. It is m a square divided by 2 because it is a disk of mass m, and for the bigger disk it is 4m, its radius is 2a square by 2. So when we solve it, we get it as 17 ma square by 2 as the value of I1. Now we have to get the value of I2. So I2 is the moment of inertia of the two disks about the second principal axis. For that, you know that we have to make use of the parallel axis theorem. So let's use parallel axis theorem for the smaller disk, and we know that for the smaller disk about this axis, the moment of inertia is ma square divided by 4. So if we write the expression for smaller disk, it is going to become ma square divided by 4 plus mass of the smaller disk into its distance from the second principal axis, which is this distance that we already know. It is equal to 4L by 5. So it is going to be 4L by 5 whole square. So this is the moment of inertia of the smaller disk about the second principal axis. Similarly, we have to write moment of inertia of the bigger disk about the same principal axis. So we get it as 4m, which is the mass of the bigger disk, 2a square by 4 plus mass, which is 4m times distance between the diameter of the bigger disk and the second principal axis, which we know it is equal to L by 5. So it becomes 4m mass times L by 5 whole square. So this I2 is the moment of inertia of this entire assembly about this second principal axis. So now we have to get the value of omega 1 and omega 2. Omega 1 is the angular velocity of this entire assembly along the first principal axis, which is going to be equal to omega minus component of omega by 5. Well, the component of omega by 5, we will require the angles over there. We already know that this angle is theta. This angle will be 90 minus theta, and this angle will be theta. So the component of omega by 5 will become omega by 5 sine theta along the first principal axis. And we already know the value of the sine theta is 1 by 5. So when we put it there, we are going to get the value of omega 1 as 24 omega by 25. Similarly, we will get the value of omega 2. So for omega 2, you can see that there will be no component of this omega along the second principal axis. There will be component of omega by 5 only, which is going to be equal to omega by 5 cos theta. and the value of cos theta is under root 24 by 5. So when we put it there, omega 2 is going to become under root 24 omega by 25. So you can see that we got the value of omega 1, omega 2, I1 and I2. All you just need to do is to put all these values in this equation. That means angular momentum with respect to center of mass will be I1 omega 1 1 cap plus I2 omega 2 2 cap. Then you are going to get the value of angular momentum with respect to center of mass. And if you are interested in its magnitude, then it is going to become I1 omega 1 whole square plus I2 omega 2 whole square under root. And you can see that definitely the calculation part is going to be very much difficult. So I'm not solving it. You have to solve it on your own. Now see, we can also visualize it in an alternate way, that we are trying to calculate angular momentum of this entire assembly about the center of mass, and the frame that we are choosing is also rotating about the z-axis, and the angular velocity with which the frame is rotating is omega by 5. So if you visualize it, it is going to be like this picture, that this is the x-axis with respect to center of mass, and this is your z-axis in the COM frame. And you know that where will be your y-axis, which is going to be into the plane of the paper at this moment, and this entire frame is rotating about this ZCM with an angular speed omega by 5. So if you visualize the COM frame which is rotating, then you will see that in this frame the entire assembly is going to have only one angular velocity, that will be in this direction, and you know what it is equal to omega. So in this particular frame, what you are going to visualize, you will visualize that the two discs which are mounted on this axle are rotating with an angular speed omega, but the axle is not rotating, because you are also rotating with respect to this axle with the same angular speed. So you will not observe any rotation of the axle. And this is the reason why you are going to observe only one angular velocity of this entire assembly. So if this is the case, it is going to be very easy, because it is a case of a single angular velocity, and definitely we can make use of this formula, that angular velocity with respect to center of mass will be equal to ICM omega vector. And ICM will be the moment of inertia about the axis that passes through the center of mass and is along this omega vector. So that axis is going to be this axis, which was our first principal axis in the previous case, and about this principal axis we already know the moment of inertia is 17 ma square by 2. So now if we calculate the magnitude of this angular momentum, it is going to be ICM times omega, that is 17 ma square by 2 times omega. So now if you check this option B, in which the magnitude of angular momentum about the center of mass is given as 17 ma square omega by 2. So now the question is whether we should mark this option as correct or not, because if we consider the COM frame as rotating, this is going to be the angular momentum. But if we do not consider the COM frame as rotating, then we are getting some other answer. So for this, IITs have given two answers. That means either you mark only D as correct, or you mark B and D as correct. In both the cases, you are going to get your marks. However, what you should do in future? Well, in future, I think you should go by this approach, that when nothing is mentioned, obviously you cannot take it as a rotating frame. For that, you have to consider it as a non-rotating frame, and for that, option D only should be the correct answer to this question.